All right, so last time when we had a discussion about chromatography, we said that things need to be Gaussian shaped. And as long as things are Gaussian shaped, then we're pretty good to go. We said that some of the bands will be much wider than the others. And there's certain things that happen inside of the column that allow the band broadening to happen. And some of those we just can't control. So we know that we're not just going to see a line. There's actually going to be a peak or a mountain shape that happens on the chromatogram. And inside of the textbook, maybe the chemical analysis textbook that you have, up here at the top, this is your traditional chromatograph itself. And there's one peak here, which means there's one component. So what they've done is that they've labeled T sub m or T sub 0. And this is the dead time or the time for the mobile phase. And if you look, there's a very narrow little signal that's right there that's pointing up. And that's typically going to be in the front end of your chromatograms every single time. It's either going to be pointed up or sometimes it's going to be pointed down. But that's the T sub m. And then here's the T sub r, and that's going to be the peak retention time. So the raw retention time from when the injection started at time 0, when the injection valve turned over and put your sample into the column, how long did it take, point blank. So that's T sub r. And we said that, depending on the length of the column and the instrumentation settings, the T sub m and the T sub r can be subtracted from each other to give us the true adjusted retention time. Because there's a little bit of time here in the very beginning that it takes the mobile phase to go through the instrument. And some people do not want to count that time because it is what we would call dead time or hold up time. In diagram B, you see a Gaussian curve. And this is what we were talking about in the previous video. And down here at C, this is a Gaussian curve that's kind of been enlarged up a little bit with some statistical parameters on it. So this peak shape basically is what we would want to see in a chromatogram. It's very even. The left-hand side is even to the right-hand side. And there's a couple of measurements that we can use and statistical parameters that we can use to make sure that it is Gaussian shaped, meaning that here at the peak, that is the retention time, and we can do a standard deviation, and we've got 1 standard deviations and 2 standard deviations and 3 standard deviations that can come from it. We can go in and measure widths at the base, widths at half heights, a whole different number of things that we're not going to talk about. But I just need you comfortable with the idea that there are statistical parameters around the whole concept of having a Gaussian shaped peak. It's kind of important, and we want Gaussian shaped as much as we can. All right. Here's an actual chromatogram of 2 components from each other, and this is really kind of what they would look like in the field. So notice they are not Gaussian shaped at all, right? These peaks go up and they come back down. The left-hand side is not exactly like the right-hand side. We now know 3 reasons why that can happen and why these bands are getting a little bit fatter. So this is more of what I would say a working chromatogram in real life situations. This would be a chromatogram that you might see in a textbook or in theory class, but you rarely will see them that way. Okay. Here in the very beginning, you actually see kind of the dead time, and you see that little dip that's happening right here. So that looks like a 6 to 7 minute dead time or hold up time for the mobile phase. And if I wanted to do adjusted retention times, I could. Another reason that I like to show you this chromatogram is because these two are the same components from each other, right? Both of these are arginine, and they give you the structure over here to the left. One is the L form and one is the D form. The L form means levo or left-handed, and the D form stands for dextro, which is right-handed. So chromatograms actually have the capability of separating two identical molecules. one with a left-hand version and one with a right-hand version, right? So same number of nitrogens, same number of carbons, same number of hydrogens, same formula weight, most of the time same melting points and same boiling points. The physical and chemical characteristics are almost identical, except for the fact that one is the left-hand version and one is the right-hand version. And chromatograms have the power to even separate those very small differences from each other, which is pretty important, right? Anytime you look at a chromatogram, whether it's in a laboratory method or a journal or an SOP, you're always going to see a couple of different setting parameters that are very important. So when you do chromatography in a laboratory, it's very important for you to write down these parameters as well. Notice up here at the top, they start off with column, and they tell you what type of column that they have used in order to do the separation. So it gives you the length and it gives you the width of the column itself. And notice that when we talked about alumina, we talked about mesh grade. How large are the particles, right? So even when we get out of the silica and alumina environment and when we get into different stationary phases can also be ground up in different ways. You can have a really fine texture or you can have a larger particle that's on the inside of the column. And you're always basically going to be reporting the particle size. So for here, it's a 3 micrometer particle size. So the length of the column and then the particle inside of the column is very important. And notice they put C18. And we'll talk about what this means a little bit later on. The mobile phase, they've written down the mobile phase that they've used, of course. That's very important as well if you want to repeat what they've done. And they've talked about the injection volume. So how much did they actually put into the machine? Notice here it was 20 nanoliters. Okay, imagine that. Most of the time we use microliters as a injection volume, but these people used nanoliter. That's super, super crazy because it's super, super tiny and small. And the wavelength here was a UV vis detector. The UV portion was ran at 214. So this was the eyeballs of the detector or the machine that recorded the data as it came off. So a couple of takeaways here. You always want to write down the column dimensions and what the column is packed with. You always want to write down the mobile phase that was used for the experiment. And you always want to use the injection volume. How much did you actually inject? Depending on the detector, some have settings that you can change and some do not. But if you have a detector and the settings can be changed on it, you need to also report that number as well for somebody so they can replicate what you've done in a laboratory. Okay, so that's reporting some of the instrumentation parameters, a little bit closer look at a chromatogram and the power of chromatography, knowing that it can separate things that are that close in relationship to each other, and then a little bit of more background about Gaussian curves and what we should be seeing in a laboratory. All right. Two things that we have talked about or that we need to talk about other than band broadening. We keep talking about band broaden, Gaussian curve. The problem, though, is that sometimes my peak on the chromatogram doesn't come up and all the way back down to baseline that smoothly. And that's what we would call, of course, the Gaussian curve, right? Okay, well, the issue here is that sometimes these peaks do not look that way. And my peak could actually come straight up, meaning things are coming off now. But it's taking a little bit longer for the molecule to finally come off the column. And we get this kind of shape. Now, you know as good as well as I do that is not Gaussian curved at all, right? And then other times what can happen is that in a chromatogram, my stuff can take a little bit longer to come off, and little bit by little bit it's happening, and then all of a sudden it kind of comes off at one time, and then it goes back down to baseline. These two variants that are out there, these two are very common depending on some of the circumstances that you're running in. And I've seen these happen many, many, many different times. This one is the back end is wrong, right? And what we would call this, because the back end of it is wrong, is that we would call this a peak tail or peak telling that begins to happen, right? So there's something wrong with the back end, and it's taking forever for this molecule to come off of the column and finally flush out of the system. And then this one is the front end of the peak is now wrong. So this is actually called peak fronting. And I never really want to see peak telling or peak fronting happening in a chromatogram, right? Now, the band broadening, how wide this is, sometimes there's nothing I can do about it. And this is accepted. I know that my peaks are going to be a little bit wider. They're not going to be narrow and straight up and straight down. As long as I've got a Gaussian curve, that's all that matters. But if I get peak telling, this is kind of not acceptable. I don't want to see this. I need to go in and make some changes in my system to clean this up a little bit. And peak fronting, I don't really want to see that either. I want to go in, change some parameters, change some settings to make sure that I can get more of a Gaussian shaped peak from these things. All right, so peak telling, why would that happen in a laboratory? Well, a peak telling typically comes from too concentrated sample. I've injected too much, okay? So my concentration is too much, or my injection amount is too much. Because what this is basically saying is that the thing is coming off of the column like it should be, and it's going straight up, right? The problem is that it's taking forever for it all to come out of there. And because it's taking forever for it to come out of the column, then that means I've put too much into the column. And if I limit and I restrict that amount, then this can become more Gaussian shaped, which is what I want. So all of those problems typically are coming from too much sample, too concentrated. I need to dilute it. I need to weaken it down. Or injection amount needs to be lowered. And I need to bring the injection amount down maybe in half or a quarter and inject it again and see if my shape becomes Gaussian at that point. The peak fronting. The peak fronting is also a problem, and typically it's due to something completely different than the above case, right? The peak fronting basically means that this component, as it comes off of the column, it's taking its time, and it's taking its time in the column itself, and not everything is really coming out at one time. So whenever I see peak fronting, that traditionally means that the stationary phase is wrong. Maybe I don't need to use silica and alumina. Maybe I need to use a different stationary phase to allow this separation to take place a little bit better and to allow the molecule to interact with the stationary phase a little bit better. And I need to make that change, and I need to make that choice. If it's not the stationary phase, then maybe it's the mobile phase that's pushing my compound through as well. So it's typically one or the other. Either the stationary phase is wrong or the mobile phase is wrong, because it looks like when it actually reaches the column, it kind of comes off all at one time. So that's not a problem. It's getting to that point that's the problem. And sometimes that's taking forever for that component to go through, and it's not coming together as a cluster. So I need a better interaction. I need a better retention that begins to happen in the column. And the only way to really achieve that is through the stationary phase change or the mobile phase change. So these two I do not want. Peak telling is bad. Peak fronting is bad. I can do things to fix this to make these better. What I want is number one up at the very top, and that is a column peak that is not too wide, because I know it's going to be there, that is very Gaussian shaped and evenly distributed. Okay? So in the next video, we'll continue our discussion with more column and more separation theory. So stay tuned. Don't lose me yet, because there's handfuls of more videos that are after this one.